I want to start with a little review of Faraday's Law. So let's say we have a bar magnet. And this is sort of the first thing we looked at when we were doing Faraday's Law. Here's a bar magnet, and here is a metal ring. And I'm going to draw the ring kind of in perspective here, where the bar magnet is going to be along the axis of this metal ring. So here's the ring. And so basically the ring is in the y, z plane, and positive x is going that way. Okay. Faraday's law says EMF induced is negative rate of change of the magnetic flux, or the Curly electric field integral of that non-Coulomb electric field around a loop is negative of the rate of change of B dot n hat dA. Okay? So let's say you have a metal ring, and you're going to move this bar magnet closer. So we're saying the velocity is that way. And if I were to draw the magnetic field due to this bar magnet at the location of this metal ring, say in the center, so initially B is pointing in what direction? That way. Okay, so we draw B in that direction. What happens to the magnetic field as we move the bar magnet closer? Gets bigger, right? So that's B initial. We draw B final as bigger. Delta B is pointing that way. Negative dB dt points other direction. Okay. So thumb in the direction of negative dB dt, fingers curl around. We should get a conventional current that is induced in this ring that would do something like that. Okay. So there's a Curly electric field in here that is causing this. If I were to draw E, that would be in the same direction. There's a Curly electric field that's driving this current. Notice that this current is going to create its own magnetic field inside the loop, and the magnetic field created by that current is actually going to be pointing in the direction of negative dB dt. But when we add the two fields together, the field due to the bar magnet and the field due to this current, we still get a net field. It doesn't add up to zero. Okay, so we get, in some ways of calculating this, we often use something called Lenz's rule, which says that the flux that is induced, or the current's induced, is in such a way to oppose the change in flux. So there's a change in flux this way, and it's opposing it by creating a magnetic field in the other direction. But it doesn't exactly cancel it out. It's just opposing it. Okay. If we knew the resistance of this ring, if this is some metal bar that has some conductivity, and we know the length and the area, cross-section area, we could find the resistance, and then we could say that the EMF that's induced is equal to the conventional current times the resistance. And so we could find the conventional current in this ring by saying it's EMF over R. Okay. So we could calculate this. Now, there happen to be certain materials called superconductors. What's a superconductor? Anybody know? It's a material with zero resistance. That's right. And it's not just close to zero. It's not just approaching zero. It really, really is zero. And what happens is that there are particular materials which we know that mobility, for example, changes with temperature. Okay, we've seen how if you have if you're plotting, say, resistance versus temperature, then because the mobility is increasing with temperature, the resistance would, or decreasing, I should say, with temperature, the resistance would increase with temperature. But it turns out for some materials you can reduce the temperature and reduce the resistance, and you reach some critical point, some critical temperature, and the resistance goes like that, bam, drops all the way down to zero at some critical temperature. Okay, this is a quantum mechanical property. We actually can't explain this using our classical model that we've been dealing with in terms of the behavior of electrons in metals. So you have to use quantum mechanics, and quantum mechanics makes these predictions, and then it's actually borne out by experiment. We can see things that have zero resistance. So what happens if this was a superconductor? Well, we run into a little bit of a problem, because if we have a zero resistance, we have EMF divided by zero, current is going to be infinite. That doesn't make any sense, okay? That doesn't make any sense, okay? So it turns out we can't actually, the analysis doesn't quite work this way, okay? What happens instead is that for a superconductor, you end up with a superconducting ring. Let's do this one first. Superconducting ring. You actually get a zero non-Coulomb electric field. Okay, so ENC actually is zero. But you do end up with a current. Okay, and the current can actually flow in the ring without the presence of an electric field because there's no resistance. The charges can just happily go around forever and ever, and no thermal energy is going to be dissipated because there's no resistance in the ring. How do we know how much current it is? Well, it obeys the rule that the change in the magnetic flux is equal to zero. Okay? And so the current that gets created is such that it is going to cancel out any delta B we get from moving the bar magnet. Okay? So we have some initial flux based on the initial magnetic field. We have a final flux based on the final magnetic field. We're going to get we have to have a change in flux that is zero, so we have to have basically a magnetic field due to the ring in that direction such that when I add up the flux due to this plus the change in flux here, we get zero. So there is no change in flux. Okay? And the only way to produce that magnetic field is to have a conventional current flowing around in the direction that we just drew. Okay? So Faraday's law is still satisfied. Okay? We still because basically we end up with d flux dt is equal to zero on this side of the equation. No net flux is changed. If there's no net flux change, then this side is zero. We don't get any non-Coulomb electric field, but yet we still have a current flowing, which is, again, kind of interesting, kind of peculiar, but it actually does happen. And if we can get this current flowing, we can keep it flowing basically forever as long as we don't change the magnetic flux because there's no resistance. Okay? So here's another example of an application of superconductors. Now you might think we could apply the same kind of reasoning to a disk. So instead of a superconducting ring, I'm going to have a superconducting disk. So this is a solid disk with some thickness. And I'm going to do the same thing. Here is a bar magnet, north pole, south pole, and the initial magnetic field is pointing that way. You might say, okay, maybe the same thing happens here. I have some initial magnetic field. I move the bar magnet closer. I have some final magnetic field, but I get some currents that are induced somehow in the edge to make the change in flux equal to zero. Well, it turns out it's even more it's different even still. Let's put it that way. It's not just that the change in flux is equal to 0. For a superconducting disk, the total magnetic flux has to be equal to 0. Not just the change, but you just can't have any magnetic flux in there at all. We say that the superconductor essentially expels any magnetic fields or any magnetic fluxes from its interior. Okay, so I don't even have to move the bar magnet now. Even if I just have the presence of this magnetic field due to the bar magnet, the disk itself is going to have surface currents, essentially surface currents, because we know again, or there's no net electric field inside, and there's got to be currents on the edges or on the surfaces induced in such a way so that if this is B of the bar magnet, and at the same location we have to have B of the disk pointing in that location. That's true everywhere. We sum it up over the entire disk. The net magnetic field inside has to be equal to 0. Okay? And that's kind of interesting because some really strange things can happen. Let me draw our disk again in a slightly different picture. Let's say I have again, let's draw the North Pole like this. North Pole down, South Pole up. Here's the disk. Okay. So the North Pole creates a magnetic field pointing down that way. B of the magnet. B of the disk has got to be pointing up. And so the disk essentially is behaving like a magnetic dipole itself now, right? And so if I were to look at the magnetic field up here just due to the disk, it's got to be pointing up. So anywhere above the disk, the surface currents in the disk are making a magnetic field pointing upward. Well, what does it kind of look like? If you have something where above it, the magnetic field is pointing away from it, this kind of behaves like what? A magnet, right? And what pole of the magnet would be essentially on the top here? North pole, okay? What's going to happen if I bring a north pole from this bar magnet near the north pole here? It's going to repel, right? You might say, well, it might actually torque the thing around. Maybe it repels in such a way that's a little bit unstable, and it flips the direction, okay? And so now the south pole is here, but now the south pole is making a magnetic field due to the bar magnets pointing upward. But I still have this rule for superconducting disks that the net magnetic flux inside has to be 0. So now the disk itself is making a magnetic field pointing down to cancel it out. And again, it behaves like a dipole, so it should be making this magnetic field even above that location or at the bar magnet's location pointing downward. So that's B of the disk. So now it looks like a dipole, but the top is behaving like what pole of a magnet? Looks like a south pole. And if I bring two souths together, it should repel. So no matter what way I flip the bar magnet, I should get a repulsion. I should actually be able to see levitation. I might be able to actually see this thing, the bar magnet, just float due to the interaction with the superconductor. So let's try it. Let me see if I can focus this. Can we see it? Does it look clear? Okay, so what we've got is this here is a superconductor. It's just a superconducting disk. It's made of some, I don't even know what it's made of, some exotic ceramic material. But it only gets superconducting if it is cooled to a low temperature. So there's some critical temperature, some cold temperature, at which point the resistance really goes to 0. This here, I don't know if everybody can see that, this little cube is actually a bar magnet. Very high magnetic dipole moment. It's one of these very strong rare earth magnets And I can prove it's a bar magnet by it sticks to the steel on the back of the, if I can take it off again, it's really strong. And if I place it here on the superconductor, it just sits there, nothing happens. Okay, let me bring it into focus here. It just sits right on top, nothing happens. So I need to cool it down to the superconductor down to the critical temperature below. And I'm going to do that with some liquid nitrogen. So let me move this aside, and let me get the camera out of the way just a second. So this is just a what's called a dewar. It's basically a thermos, okay, a insulating container containing liquid nitrogen. And so I'm going to pour some in here. And if it spills everywhere, that's okay because it's just nitrogen. It'll just evaporate. Let it boil off a little bit. Pour a little bit more. All right, let's see if we can focus this again. Can we see it or no? Down? There it is. Is it focused? Past it? A little more? There? Okay, all right, let's see if it works. Let me see if we can boil off some more off the top here. Let's see. Oh yeah, can you see it? Ah, fell off. Problem is this thing is warping. The container's warping and it's not level anymore. There we go. Can you see that? It's out of focus. Got it? And let me give it a little spin here. So no matter what direction the bar magnet is pointing, we get complete expulsion of the magnetic field inside the superconductor, which means that the superconductor is making its own magnetic field in such a way as to always repel the little floating bar magnet. And that's superconductivity. So just sort of another application of Faraday's law, but in order to fully understand the details, again, you need to really go into quantum mechanics, which we don't have time to do, unfortunately. But it's just kind of a fun last day little demo. So that's all I wanted to show. Questions on this? Yeah. That's a good question. I don't know. I have to think about that. Why doesn't it torque? So you should be able to get it to, you say, just get spinning on its own. Let's see. What end here is actually the pole? That's a good question. Let me see this for just a second here. See if I can determine. Okay, I think what's happening here is it's reaching sort of most stable point by actually having I think what it's doing, it's kind of arranged this way. It's when it settles down, it looks like that. Okay, and when I'm spinning it around that axis. Okay. So it sort of has already torqued itself into a position where it's most stable, and then if I spin it that way, it doesn't change the magnetic field, so it's happily going to just spin, spin, spin without any forces on it. I think that's what's happening here. Can we see it? Other questions? Whoop, there it goes. Fell off. Okay, questions on anything else? I'm here for the duration. So yes. Yeah. Yes. Now you need a gravitational force to. I mean, it's sitting here floating because there's a balance between the gravitational force downward and this magnetic force that's pointing upward, right? But if there were no air, yes, if there were no air, I could spin it, and there would be no air resistance to slow it down, so it should just happily spin and spin and spin without slowing down. Yeah, if it were in vacuum, yeah. Mm-hmm. But of course, you can see that this would be a fantastic way to travel, right? I mean, hence people trying really hard to think up maglev trains and things like that, where there's very little resistance between anything, really. I mean, basically it's just air resistance at that point. But the whole problem with superconductors is that you need to cool them down. So the holy grail is finding a room temperature superconductor, which people have been working on for a long time but never not been able to do it yet. I don't know what I'm not quite sure what the highest temperature superconductor created is at this point. That for a while just kept going up and up and up, and I'm not sure what the current progress is. But clearly this is one where the critical point is the critical temperature is around the temperature of liquid nitrogen. And liquid nitrogen is fairly easy to make. I mean, it's I can't remember what's the freezing point or boiling point of liquid nitrogen. Is it 70? 77? Thank you, Jeff. 77 Kelvin. And so that's not hard to create. Now, for a while, the things that in the early days you needed liquid helium or something like that to actually create superconductors, which the critical temperature of helium is what, 4? Boiling point of helium is like 4 Kelvin. It's ridiculously cold. Okay, so getting it to liquid nitrogen point, we could actually do laboratory experiments, but it's still not feasible for large scale practical applications such as maglev trains. So the quest continues.